In this lecture, we are going to start looking at the depth-first search graphing algorithm. This algorithm is going to start at a root node, which we are going to pass into it, and then it's going to explore as far as possible along each branch before backtracking. So there's a couple of things that we need. The first thing we need is a starting vertex. And the second thing that we need is to make sure that we track the vertices that we have visited. So make sure to track visited vertex. So we can create a simple graph, and we'll say A, C, B, and then we will connect both to D. We'll go from D to E, E to F, to G, back to E. And we will take E to H, H will go to I, J, and K. K will go to L, and L will connect back to E. So A will be our starting vertex. So we will go A, and then we can either go to C or to B. We will pick B since it shows up first in the alphabet. So we will go A to B, D, E. From E, we can go to H, L, F, and G. So we'll go F to G, following the same criteria as before with what character shows up first. And since we're at G, we don't go back to E this way, we backtrack, so we go from G to F, back to E, and from E, we now go to H, which we will now be able to visit I, J, and K, and from K, we can get to L, and from L, we see that we're back to E. Well, we go backtrack now, so we go L to K, to H, to E, to D, to B, to A, and the last vertex we need to visit is C. So now we finally make it to C. So as you saw, what we did there is we started out at our starting node, and we tried to get as deep into the graph as possible to visit all of our nodes before we branched out from A to our other C. So that was the last node, the last vertex we needed to visit. If we look at one more, we will say 1, 2, 3, and then from 2 we will go 4, 5, 3 will go to 6, and 3 will go to 7. So if we start out at 1, we will say 1, 2, and then we will visit 4 and 5, and now that we have hit all the vertices over here, we begin backtracking. So we'll go from 5 to 2 to 1, and now we'll go to 3, and now we can hit 6 and 7. And what we'll do with this graph is this will be our test graph when we begin testing our depth-first search implementation in the next lecture. In this lecture, we will begin implementing in the depth-first search algorithm. In the previous graphing section, we used an adjacency matrix to create our graph. What I want to do to provide you additional examples of how to create a graph, we are going to use a non-adjacency matrix based graph. So let's go ahead and start setting this up to see what it looks like. So we will derive a few traits in, such as copy, clone, partial equality, EQ for equality, and hash. And now we will say pub struct vertex of type U8. And now we can copy and paste this, put it down again, and instead of vertex here, we will create our edge. We will now derive clone for our graph. So we will say pub struct graph, and we will say vertices are going to be a vector of type vertex, and we will say edges are going to be a vector of type edge. And we're going to allow dead code. That way we can get rid of these yellow squigglies. That way we don't see them just kind of throughout our code. Alright, so now that we have our graph here, we could begin implementing in some of the methods that we saw in our previous section. So we will say impl graph, and we will say pub fn new. We'll say vertices, which are going to be of type vector vertex. We will have our edges, which are going to be a vector of edge. And we are going to return self. And here we will create a new graph, vertices, edges. So now we need to implement in a couple of traits. And the traits that we need to implement in are the from and into traits. And these traits are inherently linked, and this is by their natural implementation. Because if you are able to convert a type, let's say type A, from type B, then it should be easy to convert from type B to type A. So let's see what this implementation looks like. So we'll say from U8 for vertex. Then we want to implement the from method that says item of type U8 self, and we want to return vertex of the item right here that we passed in. So now we need to implement in a couple of methods for our vertex struct. We want to get the value back, so we'll say pub fn value, pass in a reference to ourself, where we return U8, and we return the value in our vertex. And lastly, we need to get our neighbors. So again, we will say self, and we need our graph to be able to evaluate our neighbors. We will say graph. We will bring in a vec dq vertex, and then here we will say graph dot edges dot iter filter on our edges, where edge equals self. And now we want to map our edges e.1.into and collect. And let's do a cargo format to clean that up. Alright, so that looks pretty good. So now we need to do the implement from for our edge as well. And let's see why we have an unfriendly everything looks good so far. So we will say impl from, we will say U8 to U8 for edge. We will say fn from item of U8 U8 self, and here we will say edge item dot 0 item dot 1. and both of those look good as well. Alright, and we are unhappy because we need to add in our other U8 here to make our tuple struct satisfy what it's looking for. So let's see what we're looking for here. Because of return type, so we have self, graph, and graph, vectq of vertex graph dot edges dot iter dot filter, where we pass in e into the closure, where e dot 0 is equal to self dot 0, and we pass in e at e dot 1 dot into. We don't want that there. We want it right there. And now we can cargo format it. Alright, perfect. So now we cleaned all of that up, and we've set up our graph successfully and all of our tuples for our vertex and our edges. So everything there is looking correct. So there's one additional collection that we need to bring into scope, and that is going to be our hash set. So now that we have hash set brought into scope, we can begin implementing in our depth first search. So we will say depth first search, and we're going to pass in a graph, and it's going to be a reference to a graph, where our root is going to be a vertex and our objective is also going to be a vertex. And what we're going to do is return an option that contains vec of type U8, and we want to return an optional with a vector with a history of vertices visited, or a none if the element does not exist in the graph, right? So we can have the solution, the depth first solution, but imagine if we pass in an objective or a root that does not exist in the graph. Well, then we would want to return a none in that case. So we can create some of our vectors. We can say let visited, and this is going to be a hash set of type vertex, and here we will say hash set new. We need to keep our history, which is going to be a vec U8, and we're going to create our new vector. And lastly, we're going to have our queue, which is going to be a vectq, and we're going to go ahead and initialize that as well. So in our queue, since we know our first element is our root element, or our root vertex, we can go ahead and push the root vertex into the back of the queue. And so while there's an element in the queue, we need to get that element out of the queue. So we can say while let sum current vertex, and then we want to say queue dot pop the front. So now we can add this into our history and say current vertex dot value. And now we want to verify if this vertex that we just popped is the objective. So we will say if current vertex is equal to objective, then we want to return some history. Otherwise, we need to go over all of the neighbors of the current vertex. So what we can do, and to get rid of these squigglies, let's return none here. That way everything is happy. Let's spell visited right. Visited. Alright. And now, again, we need to go over all of the neighbors of our current vertex. So we could say for neighbor in current vertex dot neighbors and pass in our graph dot into iter dot reverse. So what we want to do is, and I'll go over Rev in a second, is we want to insert in the hash set of the visited nodes if this value does not yet exist. So we will say if visited dot insert neighbor, then we want to push it into the queue, and we will push neighbor into the queue. Okay, so we have cannot find value in scope. Let me take you out and let's do a cargo format. Alright, so it looks like we have another error here. What is our current error? Cannot borrow queue is mutable as it is not. That would help as well. So we will make that mutable. Okay, so now all of our errors are gone. And so again, we return none if all the vertex or if all the vertices are visited and the objective is not found. So I said we were going to go over this reverse.rev really quickly, and it is a double-ended iterator, and a double-ended iterator has one extra capability over something that implements an iterator. It is the ability to take items from the front and the back. Right? So this is useful for us since we need to backtrack. So this allows us to make sure that we're going both ways with our iterator. That way we can go, again, as far deep on that branch as we can, and then also be able to iterate the opposite way as well. So our depth first search implementation is looking pretty good. So we're starting out at our root value, putting it into the queue, popping it, seeing if we are at our objective already, and then if not, we are going to visit all the neighbors and add them into the queue as well, and then perform the exact same operations. That way we can ensure that we are visiting all the vertices. So in order for us to test this, we're going to use the graph that we did in the previous lecture. Mod test. We will use super to bring everything into scope, and we will create our test case where we test depth first search. So we will say let our vertices equal a vector of 1, 2, 3, 4, 5, 6, and 7. And now we need to create our edges. Let edges equal a vector, and we will connect 1 to 2, 1 to 3, 2 to 4, 2 to 5, 3 to 6, and 3 to 7. 3 to 6, and 3 to 7. Close our parenthesis there, get rid of this extra one. So now we have our edges as well. So now we say let root equal 1, let objective is equal to 7. Our correct path is going to be a vector, and our path, if you remember correctly, is going to be 1, 2, 4, 5, 3, 6, and 7, which we found in the previous lecture. And now we will say let graph equals graph new, and here we will say vertices dot into iter dot map, and now we want to map each vertice into and collect. That way we turn our vertices into U8s. And now we want to do our edges for the same thing. So into iter dot map our edges e dot into dot collect. And I believe I am missing a parenthesis right here, which means I have an extra one right there. Okay, so everything's happy now. And now we can say assert equals our graph, our root dot into, our objective dot into, and I need to obviously put all this inside of the depth first search function. So for us to do that, we will quickly correct that. And we will say sum correct. That way we can compare it. So now if we run cargo tests, we expect a success to be printed out, and that was what we got. We got our success returned. So again, we implemented in a non-adjacency matrix graph just to show a different way of implementing in a graph. And then for depth first search, we use a queue to start out at our root node. We pop from the queue, push that into history, because that is what we are going to return once we hit our objective. If we do not ever hit our objective vertex, we return none. And then as long as we're not at our objective vertex and still have vertices inside the queue, we need to visit all the neighbors. And we do that in this block of code here. So hopefully this made good sense. If you have any questions on my implementation on depth first search, please feel free to ask them in the Q&A section, and I will see you in the next lecture. In this lecture, we are going to begin discussing breadth first search. So unlike depth first search, breadth first search is going to, again, start at a tree root, so some arbitrary node, and then instead of going all the way as deep as it can, it's going to fan out first. So it's going to explore all the nodes at the present depth prior to moving on to the nodes at the next depth level. So that's the difference between depth first search and breadth first search. Depth first tries to go to the end. Breadth first fans out and hits all the nodes at the current depth before continuing on. So to keep it congruent, let's go ahead and recreate our graph from the previous lecture. So we had A, C, B, we have D with both of these funneling to it. D goes to E, which goes to F, and this goes to G, or to G back to E. We have H, I, J, K, and then we have an L here, which connects back to E as well. So we are going to start at A, and then our visited is going to be like this. So we'll go from A. From A we can go to C. At the same depth we also have B, so we can go from A to B. From C and B they both go to D, so that's an obvious one. D can only go to E. And now E can go to F. E can go to H. H can go to I. H can go to J, and H can go to K. So we got I, J, and K. So Also at E, we have G, and lastly, we have L. So overall, this concept shouldn't be too challenging since we have a really good idea of how depth-first search works. Again, the key difference between depth-first and breadth-first is that depth goes all the way from A to down here as quickly as possible without worrying about branching out. So we went A, B, D all the way to L before we even got to C in depth first, whereas breadth first, we look at everything that's on that depth level. So we had A, C, but we also had B, then we went to D. So that's the big difference between depth first and breadth first. So what we can do is now we can go implement in our own solution to breadth first and run our test cases on it to see how it will compare to depth first. And we will begin implementing in breadth first in the next lecture. In this lecture, we are going to implement the algorithm breadth first search. Now, this implementation is going to be pretty similar to depth first search, but instead of our algorithm going all the way to the end of the graph, we want to fan out and hit all our neighbors at that current depth. So let's see what this would look like. So we can say pub fn breadth first search. We want to pass in our graph. We want our root vertex, and we want our target vertex. And just like in depth first search, we want to pass back or return an option with a vector containing U8s. We want our visited, which is going to be a hash set of vertexes, and we want to create a new one. And we want our history. And lastly, we need our Q, which is going to be a vec dq. And we need to make our Q mutable. Alright, so we want to say we've already visited our root node, since that is where we are starting out at. And we want to push back our root node. And then we can have our while loop. So we have our current vertex again, and we are going to pop the front of our Q. Alright, so now we have our history dot push our current vertex dot value, which we did in depth first. And then if we reach the current goal, we want to return our travel history. So if current vertex is equal to our target, return some history. Otherwise, we need to check the neighboring nodes for any that we have not visited yet. So we could say for neighbor in current vertex dot neighbors of graph, if visited does not contain our neighbor, then visited dot insert neighbor and Q dot push back our neighbor. That way we're getting all of our neighbors at that current depth. And then otherwise, if we don't ever find our target and all nodes were already visited, then we can return none because it is not inside of our graph. So again, looks very similar to depth first search, but instead of us iterating all the way to the end, we just look at all the immediate neighbors, visit those, see if it's the value that we're looking for. If not, then we can go up one more depth. So we can now add in some of our test cases, and let's keep our test cases the same. So we'll say test fn, and we'll call it breadth first search, and we'll call it fail. And what we can do is actually come up here and we can create the same test cases that we were already doing. So we're looking for a value here that does not exist. So now we can say assert equals, and we can say breadth first search, pass in our graph, pass in our root dot into, and pass in our target dot, or not target in this case, objective dot into, and we want to see that it returns back none. And then our other test case, we want it to actually find something, so we will say take all of this, copy it down, and say fn bfs found. Copy all this in. We will change our objective to 7, and in this instance we will say breadth first search, and we can say path here, and we can say let path equals a vec, and we expect our path to be 1, 2, 3, 4, 5, 6, and 7, because we expect 1 is going to connect to 2 and 3, so we expect 1, 2, 3 to be visited, and then we see 2 connects to 4 and 5, so then we expect 4 and 5 to be visited, and then 3 connects to 6 and 7, so then we expect 6 and 7 to be visited, so we have 1, 2, 3, 4, 5, 6, and 7. So let's run cargo tests to see how it looks, and it says we expected an enum option, found our vec. Oh, we need to put some around our path. And the dreaded forgot semicolon. There we go. And we see that breadth first search fail and found both ran successfully. So it's safe to say that our breadth first search algorithm is also successfully implemented in. And again, you might have noticed that breadth first search and depth first search are extremely similar, and that is because they are. So again, the big key takeaway here is that depth first is going to go to the end of the graph, and then it will work its way back to visit any nodes that it may have missed, whereas breadth first is going to fan out, meaning it'll get every single vertex at that current depth level before moving on. So if you have any questions about depth first search or breadth first search, please feel free to ask them in the Q&A section, and we will look over one more graphing algorithm known as Dijkstra's shortest path, and we will begin talking about that in the next lecture. In this lecture, we are going to go over Dijkstra's algorithm. Dijkstra's algorithm is used to find the shortest path between nodes in a graph, which may represent, for an example, something like a road network. So let's build us out a simple graph here. So we'll have node 1, 2, 3, and 4, and we'll connect 1 and 2 with 6, 2 and 3 with 3, 1 and 4 with 1, or 3 and 4 with 1, and 1 and 4 with 1, and we will connect 1 and 3 with 4. So let's say we want to start out at node 1. So we will say our starting vertex is 1. And we want to find the shortest path to 3. And well, this might be something that, we obviously already kind of know how to do just by looking at it. But let's walk through it just to see what we can do for us to get to 3. Well, if we start at 1, we see that we can go, and let's say we'll have paths here. So we start at 1. Let's say we go 1, 2 to 3. So 1, 2, 3. Well, that would be 6 plus 3, so our total weight for that would be 9. Let's say we went 1, 4 to 3. That would be 2. And then the other one is 1 to 3. Well, that would be 4. So obviously our answer to this would be 2. Well, what if we wanted to go 1 to 2? So we could go 1, 2, and that would equal 6. We could go 1 to 4, 1 to 4, and that equals 1. And then we can go 4 to 3, and that equals 1. And then we can go 3 to 2, and that equals 3. So then we would be 3 plus 1 plus 1, and that equals 5. Our other option would be 1 to 3, and that equals 4, and then 3 to 2, and that equals 3, which equals 7. So we know that 1 and 2 are out, and now 1, 3, 2 is out. So our shortest path for 1 to 2, so from 1 to 2, our shortest path would be to 1, 4, 3, 2. So that's basically how Dijkstra's algorithm works. We are evaluating the weight of the edges between all the nodes, and we are going to evaluate all the possible paths that we can have and determine which one has the lowest weight, and that'll be the most efficient path for us to take. So in the next lecture, we're going to see what it looks like to implement Dijkstra's algorithm and then run some test cases so that we can see it working in action. If you have any questions about Dijkstra's algorithm and how it works, please feel free to ask me in the Q&A section. In this lecture, we are going to begin going over a possible implementation for Dijkstra's algorithm. Now, there are many ways that Dijkstra's algorithm can be implemented, so I encourage you after this lecture to potentially think of other ways and methods that we would be able to implement in this algorithm. So before going over the implementation, we need to do a bit of setup. The first thing that I want you to do is just go ahead and comment out everything that we did from depth first search and breadth first search. That way we don't have any conflicting types possible. And then once you do that, we need to do a bit of setup before we can begin implementing in the Dijkstra's algorithm. So the first thing that we need to do is bring some stuff into scope. So we're going to bring in ordering, and then we're also going to bring in the binary heap collection. Next, we want to derive a few things for the struct that we're going to create. We're going to derive copy, clone, eq, and partial equality. And now we can create our struct, and we'll call it state. And it's going to have a field of cost of type usize and position of type usize as well. So now we want to implement ord for state. So we'll say implement ord for state. So we're implementing ordering for state, and we will say fn compare and self, and then other with a reference to self as well, where we return ordering. And what we'll do is we will say other.cost.compare and self.cost. So you can see where this is going, where we're comparing the weight of the edge. And then if they happen to be equal, then we will just compare their positionings. So we will say self.position.compare and other.position. Alright, so we are comparing the cost, aka the weights, and then if the costs are the same, then we want to compare their positions. Alright, what do we have here? Looks like we need to implement partial equality as well. So we will say partial ord for state, and we will say fn partial compare, and it sets all of that up for us, and we will say self.compare other. So that was a really easy one for us to set up, and that one just needed to be implemented as well. So now we can set up the edge struct. So we will say struct edge, where we will have node usize and cost usize. And that's all we have to do in terms of setting up for what we're looking to do. So now we can begin implementing in Dijkstra's algorithm. So we're going to start obviously at a starting vertex, and then we're going to keep track of the distance to each node. So what we can do is say shortest path, and we will pass in our graph, and our graph is going to be a vector that a reference to a vector that contains a vector that contains the edge. We will have start, which is usize, and then we will have goal, which is also usize, and we will return an option of type usize. So what we're going to return is the overall cost for us to get from our start to our goal. And we will return none, that way we don't have any red squigglies anywhere. And so the first thing we want to do is, keep track of the distances. So we will say let mute distance is equal to vector of a type that we don't care about, and we will say from 0 to graph dot length map these values that we do not care about, and we will say usize max dot collect. So what we are doing here is saying hey, for all of our distance, go ahead and make them the max size. That way when we look at the actual distance, we get a good comparison of what we want, right? So if it's usize max, then when we compare it to the distance inside of our vector here, we'll be able to update that accordingly with the edges cost. So now we want to create our visited, and we will say binary heap new. So we know that our starting distance is always going to be 0 because that is where we're starting at, and we will push this into visited since that is where we are currently at. So we will say state, our cost is 0, and our position is start. Alright. So now we can examine the other nodes, or excuse me, the other vertices with the lowest cost. So we will say while let sum state of cost position equals visited dot pop. So now we need to check to see if the position we're at is the goal. So if position is equal to our goal, then we just want to go ahead and return some cost, and that cost is going to be our distance to get from our starting to our goal. Otherwise, if our cost is greater than our current distance, well, then we've already found a better way, so we can just go ahead and say continue. And then otherwise, for each node that we can reach, we need to check to see if there's a way forward with a lower cost going through that node. So we can say for edge in our graph with our current position, then we need to say let next is equal to state cost of cost plus edge dot cost and position of edge dot node. So if our next dot cost is less, so if next dot cost is less than our current dist next position, then we found a better way. So we will say visited dot push next, and now that we have found a better way, we will say dist next dot position is equal to next dot cost. So that's all we need to do to implement the shortest path here. And we return none still down here in the event that there is no way for us to get from start to our goal. So if we say get to some vertex that does not exist in the graph, then we want to return none because we don't have a path to it. So now we can test this out, and we'll test this out by using the graph we created in our previous lecture. That way we can very clearly identify if this is working or not. So we will say mod test, use super on everything. That way we can bring it all into scope. And we will say test Dijkstra, and in here now we can create our graph. So we'll say let graph is equal to a vec, and then inside of our vec we're going to have obviously another vec, and our vec is going to contain an edge going from node 1 cost of 6 edge of node 2 cost 4, and I need to add in that guy, indent him. Helps if I add in everything appropriately. There we go. And we will add in one more edge of node 3 cost 1. Now we will add another vector, and we can start copying and pasting to speed these up. So this vector will go from node 0 to 6, and we will go from node 2 to 3. So what we're doing here again is we are recreating our graph from the previous lecture where we learned to see how Dijkstra's algorithm worked. So now we're going from node 0 to 4. And I know we didn't have a node 0 in the previous lecture, but remember vertex indexes start at 0. So subtract 1 from all of our vertex nodes in the previous lecture. So vertex 1 would become 0, vertex 2 becomes 1, and so on and so forth. Okay, let's cargo format this just to make it easier to read. There we go. Alright, so in our node 2, technically we go from node 2 to 0 with a cost of 4. We go to node 1 with a cost of 3. And remember, it's undirected, so we want to make sure we have all of our edges going both ways. And then we go to node 3 with a cost of 1. And add a comma here. And our last node we have our edge. Oop, don't need those. Our edge going from 0 to 0 with a cost of 1, and our other edge going to node 2 with a cost of 1 as well. So let's run cargo format again. Alright, so that looks a lot better. So what we have here is, and to make this clear, this is node 0, node 1, node 2, and node 3. So here we have node 0 going to 1 with a cost of 6, node 0 going to 2 with a cost of 4, 0 to 3 with a cost of 1, 1 to 0 cost of 6. So that way you can see that it is undirected. It is an undirected graph. And again, this is the same exact graph that we did in our previous lecture. So if you need a refresher on what this graph looks like visually, feel free just to go rewatch that lecture. That way you can see what it looks like. And so now we can say assert equals, and we want to call, what did we call our function up here? Shortest path. So we say shortest path, pass in our graph. Our start we will say is 0, and our goal is we want to get to node 1. And EQ. So what we're expecting to be returned here is sum 5. So if you remember from the previous lecture, our shortest path was 1 from starting from 1 to get to 2. Our shortest path was 1, 4, 3, and then 2 to get to 2. And our weight of that was 1 plus 1 plus 3, so 5. So we're expecting some 5 to be returned here. So if we test this, we see that that is the value that we were indeed returned. So our Dijkstra's shortest path algorithm is working correctly. So if you have any questions about this implementation, please feel free to ask them in the Q&A section. And in the next section, we will start looking at some algorithms that we can use when evaluating trees.